Hi, everyone, and welcome to the cardiac output lecture of our cardiovascular section of our course for exercise phys. We are going to dive right into this with an equation. And the first thing I want you to try to keep in mind, if you're not maybe naturally a math person, or the second you see any sort of math or equations show up, heart rate starts getting up. I just want you to know you can take a deep breath and hopefully take a look at equations in a new light with a new lens, where ultimately they're just letters that explain a certain variable or a certain characteristic or something, and it really demonstrates how those two things relate to one another. So you can always take an equation that is set up in a math format and literally use words in place of the variables and make a sentence and explain how things relate to one another. Okay, so lots of information packed in a smaller space. So when we're looking at cardiac output, what we're really talking about is the amount of blood pumped per minute by the heart. Okay, so sorry about that. I was trying to get my laser pointer back. Okay, there we go. So Q is just a shortened version for cardiac output, and it's equal to the heart rate, or someone's heart rate, multiplied by their stroke volume. So the stroke volume is the amount of blood pumped out of the heart per contraction by the ventricles. Okay, so just thinking about the ventricles only again when we're speaking about stroke volume. All right, and so heart rate we measure in beats per minute. We know this. Stroke volume we measure in milliliters per just milliliters as a volume, and again, when we multiply them, that's when we get our amount of blood pumped per minute. So if you see this here, and I'm hoping this records, but if not, I'll show it in two different ways. So we have our liters times minute to the -1. All that's really saying is liters over top of minutes. So it's liter per minute or milliliters per minute, depending on how we're doing that. But typically, we'll use milliliters unless we're using a larger duration of time that we're talking about cardiac output. Then we'll convert to liters. Okay, so again, what it says is just as one of these variables go up, so whether it's our heart rate that increases or our stroke volume, we get an increase in cardiac output. So what we can do is we can actually look at this and kind of explore the relationships between the two. So we have our cardiac output, our heart rate, that's multiplied by our stroke volume. So again, let's say we increase our heart rate. So heart rate goes, let's say, from 60 to 100 beats per minute. That's a unit. What we'll see, and if we're assuming that stroke volume stays the same for each beat, we'll actually see that our cardiac output goes up. Okay, so that's one scenario. We can also look at this and say, okay, what if our heart remains beating at the exact same constant 80 beats per minute, but and for some reason our stroke volume decreases? We know because of this relationship that because it's multiplied, that if we multiply these numbers again with a smaller number for stroke volume, that our cardiac output is going to go down. Okay, these are just exploring different scenarios to help illustrate the relationship between these and how we can use equations to explain the relationship between different variables. So again, our typical cardiac output for men tends to be a bit higher, largely because they have larger bodies, and women tend to be a little bit smaller by about half liter. So that's about 5 liters per minute for men as far as their cardiac output, and 4.5 liters for women. Resting cardiac output is the same, we tend to find, between trained, so like people who have are athletically trained or exercise quite often, and untrained. So this is just so say at rest. So if you're just sitting around, for 5 minutes relaxing, it'll be about the same number, this 5 liters per minute or 4.5 liters per minute. But the difference is in trained individuals. So people that, and I should clarify with training with this, that we're mostly going to see individuals that do aerobic or cardiovascular based exercise. We'll see these changes. But in trained people, even though the stroke rate will be the same, what we'll find is they have a lower heart rate, resting heart rate, and a higher stroke volume. So I spoke about this a little bit earlier, where I said people that, like endurance athletes, have a heart rate of like 50 or lower, right, at rest. And so I'll try to make up some numbers here on the fly and see how that works out. So again, if we're going to say our Q is equal to 5 liters per minute for both people in their, this is someone who's trained, untrained, okay? So we're saying their stroke volume is the same, but in the trained individual, we know their resting heart rate is lower and their stroke volume is increased. So we can kind of see, just again, making up some numbers to explore this relationship. So again, if we say the untrained individuals have a higher resting heart rate, I think a lot of you in the lab that you would have explored this in, you're finding some pretty reasonable, normal adult resting heart rates. Generally speaking, most undergrad students are relatively young, and fortunately there's a larger percentage of you that haven't come across any chronic cardiovascular diseases yet. So because of that, it would be quite typical. But normally as you get older and there's a higher chance of chronic cardiovascular disease, you're going to see your heart rate average go up. So let's say resting heart rate is 70 beats per minute for our untrained population. In our trained population, regardless of age, it tends to be a lot lower. So let's say 50. And so why did I do this quick math exercise here for you? Well, again, it's to show that heart rate can be lower in a trained individual and still have the exact same resting cardiac output as someone who's untrained and has a higher resting heart rate. And all it comes down to is the amount of stroke volume that each heart contraction will put out, right? Okay, so hopefully that helped illustrate that concept and idea to you, and you took a little away from that. And that's also, again, I'm hoping a good way to show or demonstrate or illustrate how equations can show us relationships between different variables. Okay. Good. Okay, change yeah. Okay. So next up, we come across these concepts of diving deeper into what stroke volume is and what that looks like during the different phases of a heart contraction, and more variables that we can learn or gather from that. So again, we explored already that heart rate affects cardiac output directly, but let's look at stroke volume. So end diastolic volume, we know what the diastolic phase is, right? That's the part of the heart cycle or that relaxes and allows blood to fill the heart again. And systolic volume is the volume within the heart. In particular, I should specify and be clear about this, in the ventricles. So the end systolic volume in the ventricles at the end of heart contraction. Okay, and we can take these two numbers and we take the end diastolic number, which is going to have the most blood, in the ventricles, and systolic volume, which is going to have the least, and the difference between the two is going to give us our stroke volume. Okay, so when we're looking at the ejection fraction, sorry, I almost said factor, is the amount of blood available to be pumped to relative to. So again, it's over top if you think of a fraction. I really feel it's helpful to see these numbers written, or these variables written out this way. So what I've written here and what you see here is the same thing. So the amount of blood available to be pumped to the amount of blood that's actually pumped is the ejection fraction. And so if we think about these variables, again, end diastolic volume, so that's the total amount in the heart in a relaxed heart, in particular the ventricles, over top of the stroke volume, which is the amount actually leaves the heart. Okay, so what is possible to be ejected versus what is actually ejected from the heart. Okay, so that's what that is, and that gives us a better understanding of how the heart is working. Okay, here's an image of stroke volume, end diastolic and systolic, just to kind of see visually what's going on. So again, end diastolic volume, this is the maximum amount of blood that can fill the ventricles in a relaxed state of the heart. Contracts, then we have our systole, and then we see the least amount of volume of blood that fills the ventricles in the heart. And then the difference between the two, well, that was how much that was in here versus how much that left. Okay, and so that we can figure out the ejection fraction, or the EF, because there's still some blood left in the heart, right? Okay. All right, so we kind of have an idea of what's going on as the heart contracts, how much blood is where, and this idea of cardiac output, of the true amount of blood that we can pump around our body. But there's some things that can influence just how much blood gets pumped and when and how that occurs. Because obviously there's moments when we start becoming more active, we'll need a greater amount of cardiac output, right? We'll need a higher amount of blood circulating around our body. So one of the things that we come across is this idea of the Frank-Starling mechanism. Okay, now the Frank-Starling mechanism is this almost, it's like a cool, like rebound, sort of extra elasticy function that happens with our heart. Okay, so what will happen is, once we get an increase in venous blood return, so if you can think about our heart in diastole, so it's relaxing and filling, but for whatever reason, usually exercise, and we'll get to how this venous return occurs a little bit later, but essentially we force in a little bit more venous blood into the heart. So as it's filling up in the heart, it kind of has this fixed space, but if we push in extra blood at that point in time, the heart will actually expand more, right? We can remember from our sliding filament theory how we have like an optimum amount of overlap in the muscle fibers that cause contraction, right? So if we get to that point, we almost overstretch. There's this property in muscle that has a little bit of an elastic component to it. And that's exactly what happens when we're talking about the Frank-Starling mechanism. So we get this increase, almost overstretched kind of filling of the heart because venous blood is getting pushed in. And and essentially preloads or extra loads our heart so that when it contracts, it squeezes out more blood, right? So it's like extra load, poof, extra squeeze, or extra force contraction, okay? And so as a result, what we see from that is a lower end systolic volume. And again, just to hop back here, so end systolic, again, systolic is the contraction of the heart. We're going to see the least amount of volume in the heart after this Frank-Starling mechanism, okay, occurs. Something special about myocardium, though, so we don't just have this elastic nature of muscle, but we also have this mechanism that occurs within myocardium that stretching also adds in more calcium. And again, if you think back to what we learned about skeletal muscle, that extra calcium will allow more cross bridges to attach and for them to attach longer if there's more calcium present, right? So we get this increased contractile force across the heart, which is good, right? Again, we're trying to increase the amount of cardiac output we have in these situations, right? Okay. A couple other kind of feedback or regulatory things that will happen with our heart. So that's one. Another is if blood pressure in the aorta increases, our stroke volume decreases. So part of this, just as a reminder, the aorta is the first main artery out of the heart, right? And it kind of feeds into the coronary arteries, the peripheral circulatory system. So as the aorta, the main artery coming out of the heart, if that vessel feels extra pressure on it, what will happen is there's this little mechanism that will try to get the stroke volume, so the amount of ejected blood, to decrease a bit to try to relieve some of that pressure. Okay. And the similar fashion with the ejection fraction, or the EF, that we're just trying to decrease the amount of pressure on our arteries and blood vessels by decreasing how much blood gets pumped out of the heart. And so one of the things that exercise can do to help alleviate things like hypertension, so high blood pressure, is to exercise. Exercise helps with that. So the way it does it is it decreases blood pressure and increases the volume of the ventricles, right? So if we can have more of that Frank Starling kind of preload, we can have a better ejection fraction because our end diastolic volume is larger. And so, yeah, okay, good. Okay. So we've spoken a lot about the heart directly here, but we're going to take a little peek at kind of shifting gears over to blood flow now, and blood itself, okay? Because blood plays a pretty important part as to this blood pressure, or what sort of forces the heart needs to overcome in order to get blood to the periphery, which is really important, right? So blood flow equals the change in pressure over the resistance in blood flow. So again, if we were to set up just a little equation here, say blood flow equals the change, anytime this is a triangle, if you can't tell, so change in pressure over top of the resistance to flow. I'm just going to write that out like that. Okay. So when we see something like this, we know that if, so when I say pressure difference, sorry, I'm going to back that up again. So it's kind of the amount of pressure, how do I want to write this, sorry? So pressure of something close, so to the heart typically, versus the pressure in the periphery or far away. And the greater that difference is, the faster flow will occur, right? And you can think of maybe having a really, really long straw, and if there's very low pressure down at this end, or maybe like nothing at this end of the straw, and you blow some pop or water or something through the straw, that pressure that you're making at the one end will flow very easily to the other. Now, if you can picture someone else on the other end of the straw trying to blow some air or maybe some water back at you in the opposite direction, it's going to make it harder for you to push that, say, water through, because you're going to have a more counter resistance at the other end. So water is less likely to flow down the straw. Okay, that's that concept here. And the general resistance to flow can come through a few different ways, but one of them is going to be the vessels themselves. And the other is going to be, and vessel can happen in a couple of different ways. So it's the actual vessel wall, or it's the thickness, or we can talk about the viscosity of blood. And we spoke about that briefly when we're talking about hematocrit and sweating. And so if you get more solid blood versus liquid blood, it's going to be less likely to flow through, right? If you think of the kitchen sink and you're just, again, running water through the pipes, it's going to flow very quickly and easily. If you have a bunch of food off your plates and stuff that gets into the sink, and you're trying to I don't know, get the food to go through the drain and through the pipes, is going to be a lot harder to get everything to flow down the pipes, right? So you're going to need more pressure. Okay. So again, that kind of describes blood flow and what happens here. So again, if the difference between, let's say, high pressure and low pressure on these, the higher the pressure is on one end and the lower it is on the other, we're going to see an increase in pressure and therefore an increase in blood flow. If we were to look at vessels or viscosity, anytime the number on the bottom of a fraction, okay, so this is like a fraction, right? We have our numerator and our denominator here. Anytime something on the bottom gets smaller, it'll make this number get larger. Okay, so it's got an inverse relationship is what we call it. Now that might seem really obscure or abstract, but definitely try to understand this because it really does explain a lot of different relationships between variables when you see them set up this way. So again, one of the things here, reverse flow. Let's make this a real number just in brief so you can see that happen. So let's say, let's go 5 over 10. These are just arbitrary numbers to try to demonstrate this to you. So if I go 5 over 10 is the same as saying 1 over 2 or half. So if this is our starting point, if I decrease the bottom number, let's say by half, so I make it 5 now, that number is 1 over 1, so that equals 1, and this is half. Okay, so again, by decreasing the bottom number relative to the top number, if we keep that the same, oh my goodness, that's supposed to be 5. We make this number with the things are equaling larger. Okay? Okay. If that went by a little quick, go back, rewind the video, watch it again 1 or 2 times, pause at each step so you can understand that. Okay? Great. Where was I? Blood flow. Right. So we were talking generally about pressures and how can blood flow kind of influence that. Well, again, as the heart is contracting or relaxing, there's different pressures in our vascular system. So we'll need to take a look at systolic and diastolic blood pressures, which we did, which you did in your labs or will do in your labs, and depending on the order of things. So, but in this particular recording, you will have already done these. So with our systolic blood pressure, if you recall, that's when the heart contracts, you're going to have the highest pressure, right? And hopefully this makes sense, right? If the heart's really contracting and squeezing the blood out, you're going to feel like there's going to be more pressure within this contained system, right? Diastolic is when the heart relaxes and refills. And so again, when the heart is most relaxed, is that when we're going to have lots of pressure on our vascular system? No, it's when it's going to be the lowest, right? So we have our highest part and our lowest part of our blood pressure in our systems during the cardiac cycle. And as you know and did, you can measure on your brachial artery with a sphygmomanometer and stethoscope. That's the blood pressure cuff and stethoscope. You can measure this difference, right? Typically, as some of you found, the typical resting blood pressure for someone is about 120 over 80. But also, as many of you know, depending on who you were measuring from, if it was, let's say, some of your friends or another lab mate or younger siblings, this number is not going to be true. And depending if you've truly let the person sit and relax for a long period of time or not, these numbers will definitely not be true, right? So again, I think that's important to remind that this is typical, but by typical, it does not mean always going to be around those numbers, right? It's going to vary drastically between people. And one of the biggest differences between someone who's maybe trained or younger will be the diastolic number is going to be quite a bit lower than typical for many, okay? Especially if you did get a decent amount of time to rest, okay? Okay, so while these are the pressures that we start with closer to the heart, and again, the brachial artery gives us a relatively good indication being fairly close to the heart. The blood pressure definitely goes down as it goes through our body. So we can see here when it's close to or in our ventricle itself, we'll say that that's when we typically see up to 120. When it gets to the arteries, so now we're large arteries, brachial artery being one of these, we can still get up to 120, but that's when we'll see the diastolic. Again, we're out of the ventricle. If we were to, we're in the artery, so the periphery itself experiences a more static and less dramatic change in pressure in the vessel. But once we start getting to smaller arteries and arterioles in particular, we notice that this trails off quite a bit. So some of you, if you would have gone too far down the forearm to try to measure blood pressure, you'd probably notice generally that some blood pressures might have been getting too low. You typically don't see that because it's harder to hear, but that's one possible explanation for that. And then, of course, once we get into the capillary beds themselves, we have quite a low amount of blood pressure. Now, you can pause here in your minds and think, why might that be important? Well, if you get to the actual capillary beds and you have single cells that are very permeable, and you don't want a lot of pressure at those areas. So, because what can happen is you can actually force fluid into those areas and start bruising the area in the tissue from that, and also fill the interstitial space with extra fluid, so you get swelling. And that does happen in some conditions and pathologies. But the other thing of note, and we definitely speak about this a little later on when we speak more directly to venous return of blood to the heart, in particular some of the muscular components of how that works, is there's almost no pressure once blood gets into our veins. And that's good in one sense. For example, if you go to take blood or put an IV catheter in, one of the reasons that we always find veins rather than an artery is there's no to very little blood pressure in veins, right? So if we were to get an IV and we were looking for arteries to put them in, again, as soon as we put that needle in, what would end up happening is blood would, at a very high pressure at heart, the intervals of our heart, really start overwhelming the system, and we wouldn't be able to drain in passively through gravity-fed fluids like saline into your body because the pressure from your blood would be pushing it back out. In fact, we get blood going the other way. So again, a big difference in a reason of an importance for why we have lower blood pressure both in the capillaries and in your venous system.